Welcome to this topic that is called Poisson Distribution. I welcome you, all the students who are taking this course, that this topic is very important, especially if you are taking a course in mathematics. And you'll realize that Poisson distribution is one of the distributions that are discussed under probability. So we have normal distribution, which I believe you've learned, and binomial distribution. And then now we are going to consider Poisson distribution. So under this topic, these are the learning outcomes that you will be able to achieve by the end of this lesson. So number one, you'll be able to define the history and application of Poisson distribution. Number two, you'll be able to deduce the Poisson distribution definition, that is, from some conditions that shall have been met. You'll be able to deduce from those conditions that shall have been met to well define the Poisson distribution. Number three, you'll be able to recognize the relationship between binomial distribution and Poisson distribution, because this is one case where most students fail to know the difference. Because in exam questions, you'll find that there's a question that you've been given. You as a student, from the question that has been given, there are key factors that you'll have to consider in order to use either of these distributions. So by the end of this lesson, you'll be able to recognize which distribution is appropriate for binomial or for Poisson distribution. Therefore, now, under the history and application of Poisson distribution, first we're going to learn about the inventor. It was invented by a French mathematician and physicist who contributed. It's not the only thing that this gentleman invented. He also indeed invented very many theories in mathematics and in physics, especially in mathematics. His contribution was so much seen under pure mathematics and statistics, where in fact he developed some theories in integrals, probability theory, and calculus of variations. Under physics, we realize that he gave us theories under potential theory, under optics, under mechanics, thermodynamics, and others. So this gentleman gave us very many contributions on these two subjects. Now, under application, you realize that Poisson distribution is very much appropriate, especially when you want to consider the number of passengers that arrive in an airport in an hour. Then also, you can also consider the number of babies born in a hospital in a day. So if you look at these two cases, you realize that the time is specific. You realize that the number of passengers that come to an airport considered in an hour, they can vary, and the timing can be different. You can realize that maybe in the first 2 minutes, 10, like it's for example 10 passengers arrive. Then there is a lull. Then after that, you find in the next 5 minutes there's another 10 passengers. So here we considered time discretely, which means time as it's being counted discretely. Therefore, we can use Poisson distribution to model this type of scenario. Also, in the number of children that are born in a hospital in a day, we can know maybe after every few minutes the number of children that are born. So, using these two cases, these are just examples of applications where Poisson distribution is very much relevant. Especially, you have to consider the specific time, the specific timing that is in this, or the specific space that is in these scenarios. Next, we are going to deduce the Poisson distribution. And in order to deduce the definition, there are conditions that must be met so that a student, or you can accurately identify that in this case, in this problem, in this scenario, it is appropriate to use Poisson model. Therefore, these are the conditions. The random variable x must have these conditions in order for that problem to be appropriately used for Poisson distribution. Number one, the x should count the number of events or occurrences in a specified time or space. Number two, the events must occur independently of each other, which means no two events can happen at exactly the same time. So you cannot consider more than two events at a time. You consider one event at a time. In that time space, in that specified space, you consider one event at a time. You consider the probability of that event happening independently. For example, we can consider the probability of getting ahead from maybe 10 throws of a coin. See that? Can consider the number of vehicles that are passing at a point. See that? In a specified time. That is also another scenario where you can use Poisson distribution. Therefore, the fourth point is that the x can take any positive integer from 0 to infinity, which means this is a discrete random variable with countable infinite number of possible values. Discrete means they are countable, which means they are not in decimal. They are countable. That is why they are called discrete. Therefore, from the foregoing, we can define the Poisson distribution as a discrete distribution used to show how many times an event is likely to occur over a specified period. See that? So that is where this Poisson distribution is defined. A discrete distribution used to show how many times an event is likely to occur over a specified period of time. Now, the third learning outcome that you are supposed to consider was the relationship between binomial and Poisson distribution. You realize that Poisson and binomial distribution, they are closely related, but not so much. So in binomial, the random variable x is used to count the number of successes in a fixed experiment, and the x also takes a value from strictly 0 to the number of experiments. So if the experiments are 10, so the x, our value of x here will be start from 0 to 10. If maybe the number of the sample space is maybe 20, so the x, the random variable x will take values from 0 to 20. As for Poisson distribution, The random variable x will count the number of occurrences in a fixed space or time. So I want to underline that. That one is the number of successes in a fixed experiment, but this one, the number of occurrences in a fixed time. So the random variable x will take any value from 0 to infinity. So that is where the difference is. Then the identity is that both of them are discrete variables. Both of them are discrete, which means the values that they take are countable. So one goes to infinity, the Poisson goes to infinity, but the other one takes from 0 to the number of trials. So that is the main difference between these two. Now, as a summary, we know that the Poisson distribution was invented by Simeon Denis Poisson, a French mathematician and physicist, and is used in situations where there are several events happening in a specified time. So we can have like 20 events, we can have like 30 events, and that is the reason why you saw the random variable taking a value from 0 to infinity. So, but the time is specific. So we want to see how many events can happen in that 1 hour, and they are discrete, which means they are independent of each other, and they cannot happen at the same time. So that one we see in point 2, where the random variable x counts the number of events in a specified time, and these events can take from 0. 0 means that there is no event happening, so it can take from 0, 1, 2 to infinity. So in that specified time, several events can happen. Then these events should not happen at the same time and should be independent of each other. So number 3, we were also, in summary, is that the relationship between Poisson and binomial is that in the identity is that both of them work on discrete data, and the difference is that the random variable x counts in Poisson the number of events in a specified time and takes any positive value from 0 to infinity, while in the binomial the number of successes in a fixed experiment and takes the value from 0 to the number of trials in the experiment. Now, I want to thank you for having listened to this unit, and I believe that even as we go forward, as we are going to continue with how to work out these problems, I believe that for the introduction, you have understood what Poisson distribution is, and you can use it, and given a problem, you can be able to accurately identify that this problem is appropriate with the Poisson distribution. Thank you, and may God bless you.